Hello and welcome again to this discussion on fluid mechanics. So, we are continuing the series. If anyone has joined and started with this video only, then I suggest him or her to start with the full series from the beginning if he or she wants. Okay, so I will put the link of the series in the description. Also, you can get in the I button. Okay, so uh, in the previous discussion, we have studied about the forces on flat surfaces submerged in a static liquid. Okay, static fluid. So now let us go for the same force analysis for a submerged curved surface and not a flat surface. Okay, so what is the motivation of studying this analysis of forces on the curved and the flat surfaces? You can see in many engineering applications, you may be you may be asked to design, okay, dams, water gates. Okay, so there may be a situation that uh, let us consider that this is the free stream of water. Okay, and after that I have uh, something. Okay, where the flow rate of water has to be restricted. Okay, so then what I can do is I can make a gate. Okay, so let me draw the gate by an wooden color. So this can be my gate. Okay, okay, and the gate may be hinged here. Okay, I have the gate hinged here, and the remaining water is allowed to flow beneath this gate. Okay, okay, so then there is some force, or by any means you have to apply some force to hold this gate. Then as an engineer, you may be asked to find that what is the value of this f. You may be asked also to have a gate that is like this nature, curved. Okay, so now the water has restricted up to this place only. Okay, this place I don't have the water. Okay, then also you do require some force here. Okay, to hold the gate. So to find that force, okay, or maybe given that force that I am only capable of putting this much amount of force, but I have to find the dimension of gate. These two in I mean for these two situations you are required to have the knowledge of these forces on submerged and flat surfaces. Okay, so now let us move for the submerged surfaces. So firstly, why are we studying the submerged surfaces, the forces on submerged surfaces differently from those of on flat surfaces? So let us consider here two scenarios again. So okay, here is the free surface, and here is the flat gate. Okay, or any flat surface AB. Okay, now I am again having in a different situation a free surface and a let us say now I don't have a flat surface like AB, I have this curved surface AB. Okay, A dash B dash, let us say. So if I draw forces, okay, if I draw forces on AB, then I know I have told that the direction of pressure force is firstly perpendicular to the surface, right? And secondly, it is compressive. It is acting inwards to the surface or acting opposite to the area vector. Okay. So now let me draw the forces on the flat surfaces. So they will look like something this, right? Don't go by the obviously don't go by the size of the arrows. I am not denoting the magnitude here. I am just denoting the direction of the forces. So all these forces are perpendicular, right? All these forces are perpendicular. So now if I have to draw the forces on this curved surface, so let us say at any point I want to draw that. So let us say at this point and any arbitrary point P. Okay. So first of all, the force should be compressive and that should be perpendicular to the surface. So on any curve, how can you draw a perpendicular? So the answer is we all know that firstly I have to draw a tangent, okay, through this point. Okay, so this line is I guess uh, it 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 looks like a tangent on this point P dash. Okay, the thing is same. So just um, out of an coincidence, I have drawn a tangent on P dash. So let us consider the point P dash for analysis. Okay. Then the direction of force on P dash will be this one. Okay. Let us choose another point. Okay. Like let us choose in another point. Okay. Like this one. Okay. So here the tangent is looking like to be this, right? Approximately. Okay. So then the perpendicular force should be like this one. Okay. And let us choose another point, this. So here the tangent will be something like this, right? Then the force will be something like this. So just see the difference, see and understand. I would suggest by this point, if you haven't already catch the difference, just pause the video and look at the both of the diagrams and try to understand that what is the difference. So first of all, that you can see that for this case, let us say that this is case one and case two. Okay. So for case 1, directions of all force vectors are same, and for case 2, directions are not same. So for case 1, F total can be represented as scalar. Okay, magnitude of F total actually scalar addition of magnitudes of forces. But for case 2, if total, the magnitude of if total is not equals to the scalar addition, right, is not equal to the scalar addition of the forces, right? Okay, so this is the basic difference of force magnitude. Okay, so this was a basic requirement. So we have to add the forces vectorially and then find the magnitude of the force in case of a curved surface. So then how to calculate the force? Okay, so now let us come to our final actual topic, that is finding forces on submerged curved surface. Okay, okay, so let us continue. Then first of all, let us have again a free surface, and let us have a curved surface. Okay, so here I have filled with liquid everywhere around the surface, curved surface. Okay, everywhere it is filled with liquid. So this point A and this point B. I have to find the net force on the surface A, B. One one option can be just go for the integration. Take a particular segment elemental length, let us say this to be ds. So here the force will be something F, and what will be the force F here? So so this is not very critical actually to find, and that will be nothing but if I know this height, okay, h, then this force will be h rho g. Now for this time onwards, whenever I say that the force is only h rho g, you should consider PAT as 0, or h rho g is the gauge pressure. Okay, okay. So this is the F, and then like that you can. Okay, so this is the DF actually, DF. Okay, so DF will be this much pressure P into dA. Okay, so dF is that much pressure into dA, and we have to integrate over the whole curve, over the actual. So maybe you are given the equation of curve, that is let us say y equal to something x square. Let us say that you have this curve. Okay, so now you have also told that the width of the gate is w. What do you mean by width there? Let us say that the y equal to x square means a curve like this. Okay, and width means okay, this. Okay, okay. So this is the width that the gate is extended. Okay, and if the width is w, so then you can find a dx here. Okay, then that dx, so then that ds actually, so if I exaggerate the ds part, uh, uh, it can be approximated by a straight line, and the component of that straight line should be dx and dy, right? So at every part we do have this ds equals to root over of dx square plus dy square. If I take the dx common, then it will be 1 plus dy by dx whole square into dx. Okay, so sorry, just a silly mistake. This is ds. So then this df equals to p. Okay, ds. Okay, and p equals to h rho g. Okay, h rho g into ds. So that will be equals to h rho g into 1 plus, and if you are given the curve equation as y equal to x square, then dy dx equals to 2x. So that will be 2x square into dx. Okay, so now let us say that you are given this height as given this height as uh, small a. Okay, okay, and you are also given this length. You are also given this much length. Okay, let us say that this is l. Okay, and so if we assume a coordinate axis, okay, like this. Okay, if we assume a coordinate axis like this, let us take a different color actually. Okay, so here is the origin, this is x, this is y. Okay, so that directly means that at x equals to l, okay, y equals to l square. Okay, I have considered this curve as my y equal to x square. Okay, okay, so then also I am, so this height, so this height is nothing but l square. This height is nothing but l square. Okay, if I take any arbitrary x, let us say from here I am taking any arbitrary x. Let us say that this is the arbitrary x. Then to find the pressure on this point, on this point, okay, that is at the height x square. I I need to know this height. I need to know this height. Let us say hx. Okay. So can you find this hx? I think you can. So just see from this geometry that hx plus x square is equal to a plus l square. That means hx is equal to a plus l square minus x square, right? So just put this hx in here, a plus s a plus l square minus x square. Okay, then this much into rho g into 1 plus 4x square dx. So this is df. Now I have to integrate this force to get my actual force, F equals to the actual force, total force, from x equal to 0 to x equals to L. Okay, so this was one of the uh, this was one of the formulations or one of the ways to find the net force on a curved surface by integration. And let me tell you that you have to develop your own mathematical sense like this. So I have developed, or I have formed this mathematical problem right now here. Okay, okay, so I don't know that whether we do have a problem like this or not, but if it comes, there are many uh, easy ways to solve, and that I will uh, explain now. And those are easy, but those are very much logical. Okay, but these are the also very ingenious ways, not so ingenious actually. The ingenious ways I will describe now, but these are also the ways. Okay, and to integrate any varying quantity over a line or a surface or even the volume, so that is a very important and critical mathematical concept. In your gate examination, you can be asked in the engineering mathematics section also that is you can be that is you can be given a vector, okay, and you are required to integrate maybe over a line or a surface, okay. So okay, so my point of solving this problem like this was that just uh, try to grow these types of elementary concepts, okay, of integrating the things. Now let us move to the second approach, in which we don't have to integrate actually, but just applying the common principle of force equilibrium, we can find the forces on a submerged curved, curved surface, okay. So let us again consider the free surface, okay, sorry, let us again consider the free surface, okay. So this is my free surface, okay. So at this time, okay, this okay, so this is my free surface, okay, and now similarly I have my curved surface AB, right. So I have to give an explanation of the total forces on this curved surface, okay. So all over here I have fluid, okay, all over here I have fluid around the curved surface. So let us just give some boundaries, okay. So maybe this is, sorry, just let us change the color. So maybe this is a tank again, okay. So consider this as a tank again, sorry, okay. And now, so this tank is filled with water. So this is the free surface S1, okay, and everyone here water, or you can consider any other fluid, okay, okay, and this is the curved surface CS, fine. So first of all, let us apply the very basic Newton's law of motion on this, okay. So if I apply Newton's third law, okay, okay. So if two bodies are in contact, let us say body A and body B, okay, they are in contact, B and A, okay. So I if I consider that, so at this point A is fixed. Now I am putting some force F here. So if I have to calculate force on A, okay, force on A, then that will be minus of force on B, okay, at the contact point, contact point, right, right. So this is the Newton's third law. Similarly, now let us consider an imaginary volume of fluid or imaginary mass of fluid. So I can consider, so let me write it clearly. Let us consider, okay, an imaginary mass of fluid, okay, of which of which one boundary. Okay, or let me correct or improve the sentence a bit. Mass of fluid which has one of its one of its boundary surface common, or uh, or we can say that sticking. Okay, sticking with, or sticking, or good English should be coinciding with the concerned curved surface. Clear? Concerned curved surface. So let us now try to construct such imaginary mass of fluids. So if I consider an imaginary boundary, so let me draw the boundary by red. Okay, an imaginary boundary like this. Okay, so these are the boundary lines, and okay, so this part of the boundary line is coinciding coinciding with the curved surface. So, and these are the other boundary lines. Okay, so this is my, so this can be one of the fluid masses. So this is an imaginary fluid mass. Okay, fluid mass. Fine. But do we have this choice only? I can see another choice. Okay, let us draw another boundary, and if now, so let us choose another color to have the contrast actually with the previous boundary. Okay, so let me choose this color. Okay, so if I am having the boundary line like this, okay, okay, so for this mass also, the same part of the boundary I have, which is coinciding with the curved surface. Now this part, okay, this part, okay, is my, okay, so this is another imaginary fluid mass. Okay, okay, so let us name this as uh, imaginary mass 1. Okay, and let us name this as imaginary mass 2. Up to this, is it clear? Okay, so now let me put it side by side. Okay, okay, so then firstly consider, okay, so just I'm doing it by this color. Consider mass 1. Okay, considering mass 1. Okay, then I can say that force, okay, on curved surface by fluid is equal to minus force on by fluid mass 1 actually, force on fluid mass 1 by controls by curved surface, right? So if I have to find the magnitude of force on control surface, then I am done if I can find the magnitude of the force on the fluid mass 1. Okay, so let us now consider the fluid mass 1. Okay, I am drawing it by the red color itself. So okay, so this is the fluid mass 1. Now let us consider that the force. Okay, okay, so let us consider that the direction of force on this fluid mass in the horizontal direction is Fh, and in this direction, and the same for the vertical component of the force is Fv. So these same components, the magnitude will be applied on the curved surface, right? Okay. So how can I find this Fh and F? Now, what are the other forces acting on this fluid mass 2? So one force can be this reaction force. Okay, so this is reaction by the tank base. Tank base. Clear? Another very obvious force is its own weight. So that is W1. Okay, so that is nothing but the weight of the imaginary fluid mass 1, right? Clear? So this Fh and Fv are nothing but Fh equal to horizontal component of force uh, produced by the curved surface, and Fv is that. Okay, Fv is vertical component of that force. Clear? Of that force. That force means the force produced by control surface on the fluid mass 1. Okay. So now, considering this diagram, if I apply summation of Fx equal to 0. Okay. Okay, so I have not completed the free body diagram because I will have the pressure forces also, like this, right? So the pressure forces are always perpendicular and compressive in nature, right? So these are the pressure forces. Okay, so the vertical component will be somewhat easier. So firstly, let us consider the vertical components. Okay, so let us do this Fy equal to 0 because of equilibrium, static equilibrium. That means Fv and Wi are acting in the same direction, W1, and that will be equal to R. That means Fv equal to R minus Wi. Okay, So how can we find this I? Because Wi can be known, okay, because Wi is nothing but the volume of volume of this portion and multiplied by the density, right? So Wi can be known, but what about the R? So now come back to this figure, okay. So R is the very just be very focused, okay. So R is this reaction, right? Let me just change the color actually to avoid any confusion. So R is this reaction, okay. So now if I consider this whole this volume, this, okay, if I consider this total volume, okay, this total volume, then there are two forces only acting in the vertical direction, obviously. I am talking about the vertical direction. One is R, another is its own weight, right? Another is its own weight, and this weight is comprised by this part and this upper part. So this this weight is nothing but W1 plus W2, weight of the fluid mass 1 plus weight of the fluid mass 2, okay. And by applying the same static equilibrium equation, this R must be equal to this W. That means R must be equal to W1 plus W2. I hope I am clear. So that means this will be, that means this will be W1 plus W2 minus Wi, that is equal to W2, okay. So F vertical is equal to W2. That means F vertical is equal to the weight of the fluid mass above the control surface, okay, this much, okay. Now let us go for the horizontal force balance, okay. So that comes from summation of Fx equal to 0. Now what are the forces acting horizontally on this imaginary mass 1? So one force is this one, that is Fh, by the surface on the fluid mass. Another forces are the pressure forces. So if I consider this part only, the pressure force is nothing but what? So let us again come to this diagram. So I am considering this part only, right? This part only, okay. So at this point, the pressure is, let us say, this height is small h, and this total height is capital H, right? So the pressure acting at this point, okay, so that will be something h rho g, okay, that will be something h rho g, small h rho g, and at this point it will be capital H rho g, right? So I know this much, okay. Now my point is that, so I have said that I can find the pressure if I know the height, and at all this level, at all, I mean at this level, for all the points, the pressure is H rho g, right? So here also, for all the points at this level, there are same pressure. That means, so this pressure force is having the direction opposite to this pressure force, and this thing will hold for all the levels in this domain, okay. Okay, now only this part has an effective force, because I don't have any force, at least up to now, that is equal to, I don't have any equal pressure force like this, right? Because on this surface, the only force I have is due to the curved surface. Okay, and that is Fh. So now this much pressure force just contributing in this much area. So I am denoting this as something F Fp, that is F pressure. Okay. So that means that this Fx equal to 0 will give us Fh equals to Fp. Now, what is this Fp? So now this is easy for you, because, so if I just again draw the diagram, because everything has become a bit clumsier. Okay, so I'm drawing this again, this imaginary surface too. Okay, so that means only this part, the pressure force is significant. So how to calculate this Fp, this pressure force? So this is, I can see that this is just a flat surface, flat surface. Okay, and I know the principle of finding the force on the flat surface. That is, I have told rho g h of the centroid into the area. Okay, so I can find the centroid, that is, this will be the centroid. I have to find this height hc from the free surface to the centroid. I can find this Fp. Okay, and what about this area? Okay, because I have only this curved surface. I am drawing again and again because everything is becoming clumsier. Okay, so I have only this curved surface, and my area is this one. Okay, so how can I get this area? So if I put a torch here, okay, and I give the light rays, and if I take a screen here, okay, then the shadow will be like, so then the shadow will be something like this. Okay, so this area is nothing but the area of this shadow, or area of the projection, area of the projection on the vertical plane. Okay, I think it is clear that how to find this Fp. So Fp is nothing but this rho g h centroid into area projected. So this h centroid and this area projected, both has to be determined from this projected area. Like for example, if you have a, circular surface, okay, circular surface. So let us consider a semicircle actually. So let me remove this. So let us consider a semicircle like this. Okay. So you already know from your common sense that the area projected will be nothing but what? Also a circle of same radius, of same radius. So this is not a circular gate. I mean that is in 3 dimension. This is an half sphere. Okay, half sphere. So half spherical gate. So if I put the torch here again, so then I will have a shadow on a screen like this, and that will be a circular. So then our area projected will be pi r square, and this hc will be, let us say that that this is the free surface and this height is z. So hc will be z plus r. Okay, because the centroid is something here, so this is r. Okay, okay. So that's how I find both the fh and fv. But now, not the thing has not ended actually. Now let us consider the same analysis considering this fluid mass that is above the this curved surface. So in the video, because of the inertia of speaking, I have pronounced this curved surface many times as control surface, but don't be confused, that is my silly mistake. So there is nothing called control surface here, but this AB is called curved surface here. Okay, so now let us consider this fluid mass, the an imaginary fluid mass, that is mass 2. I am drawing again. So now I am doing it a bit faster because I have already done for one mass. Okay, so this mass is looks like something this, and we know that this surface coincides with curved surface, and this coincides with the free surface of the fluid, right? Again I am considering the same forces. Okay, so the forces which are applied by the curved surface on this fluid mass. So again, then again I can have this much fh. Okay, and so let us say that this will be the fv. So this choice of direction of fh and fv does not matter initially, because if if you consider the fh to be in this direction, let us say initially, and considering this direction, so if you get the fh value as something called negative, okay, minus 10 Newton, then you know that your actual fh direction is in the opposite. So you can start by considering any of the directions. Okay, so again, just let us now see that what are the forces acting on this imaginary fluid mass. Okay, so another forces are, I have this one, that is w2. So this is weight of imaginary fluid mass 2, right? Okay, again I have the pressure forces, right? So on on this face, pressure force is always perpendicular and compressive to the face, right? Right. So, and on the other face, I again have this one, right? Okay, okay. So these are the pressure forces. Now, similarly, I am just removing these words, okay, for clarity, because now I hope either you have written or you have understood. Okay. Now, similarly, all these levels, okay, all these levels. So, at all these levels, I have the pressure force acting in this direction and also in this direction. So, they will cancel out each other, right? They will cancel out each other. The only force that will matter is contributing, the force that is contributing on this particular area, right? And if you see, then this area, so I am again removing these lines, okay, just for the sake of clarity, okay. So if you again see that, let us draw a line here, okay. This line is not perfect, okay. This is somewhat perfect. So if you see, again I am drawing this line, so this much of area here, okay. So this is nothing but, again if you put a torch here, okay, so this is the light and this is the shadow, okay. This is the same area projected, because you see that I have shown this area, right? This area for the imaginary mass 1, and this area is same as actually this area. So that doesn't matter that if you put the torch here or in this side. So the same concept. So this was only the fluid mass 1. So I have putting the same torch at the same position, so this area projected remains same. I hope this is clear. If not, just comment. Okay. Now, if I have to consider now the vertical force, there is only weight 2. So again, for this Fy equal to 0 summation of, that directly yields F2 equals to F, and which matches with the result that has been obtained considering the fluid mass 1, right? This one. And summation of Fx equal to 0, that gives us this Fh is equals to, again, rho g hc and ap, and this hc and ap both have to be calculated considering the projected area of the curved surface on the vertical plane. So every word is important to uh, understand. I want you to understand, and at any situation, if by any chance if you forget the formulas, okay, like these formulas, okay, then I want you to derive at that place only in somewhat 30 seconds, okay. So I did not apply any concept that you did not know from your 10 plus 2 level, okay. So by those first principle, like the Newton's first law, second law, static equilibrium, right? So by only these uh, conditions, I have developed the equations, right? So these are the applications of the concepts that we all have learned in our 10 plus 2 level, actually even in the class 9, 10 level, okay. So both the analysis, considering fluid mass 1 and fluid mass 2, is giving us the same result. Then then I mean, we all have two choices for any curved surface. Then what to choose actually? So for this, I will give you some example of some problem that has been asked in GATE actually, or in your semester examination also. Okay. So let us say that this is, okay. So let me draw first the total diagram. Okay. Okay. So okay, let us consider this one only. So this is the floor, okay, and this is the free surface, okay. So here I have water, okay, and this is a gate actually, not your examination but the actual gate holding the water. So let us say that the gate is hinged about this point, okay. Now you have to, okay, so forget all the things, you have to just tell the pressure forces, okay, total, okay, total force on the part AB, okay, AB, the gate is fixed, okay, total force on the part AB, okay, okay. So how can you do this? So I am just applying the same concept. So for the, so this force has two components, one is horizontal, another is vertical. For the horizontal component, I have to make a projection on the vertical plane. So the projection will give me what? The projection will give me a, on this screen, okay, on this screen maybe. So this is the screen, okay. So the projection will give me a, just pause the video if you are not getting anything, okay, rectangle, okay, rectangle, okay. So this fh equals to rho g hc. Now what is the height of the centroid of this rectangle from the free surface? That is nothing but this, okay. So this is r by 2. So r is the, okay, okay, not r by 2 actually, so I must have given this height, okay, I must have given this height. So let us consider that this height is something 3r by 2, okay, and this is the center, okay. So then what will be the height? So the centroid of the rectangle will be the midpoint of this line, the midpoint of this line, that is this. So this distance is r by 2, okay, and this distance is nothing but what? 3r by 2 minus r by 2, and that is r, right? So that means is that r? Yes, is that is r. So can that happen? Actually not. So this height cannot be actually 3 by 2. So this is something which is more than r by 2, okay, more than r by 2, but less than actually uh, less than what? More than, I mean this height is more than r but less than 2r, okay. So just I cannot get the actual value, then I have to pose the problem, okay. So let us say that this is something z, okay, for avoiding any confusion right now. So then this part is nothing but z minus r, z minus r. So then this height is hc, this height is hc, then hc equals to z minus r plus r by 2. I can find hc, then this will be is rho g into, rho g into, okay, rho g into z minus r by 2. And what will be the area? Area will be this total height z into the width. So this width also have to be given, this width of the gate, that means this one. So the gate is like this, okay. So then this is the width, this is the width, okay, okay. So I can find this fh. So now what about this fv? Okay, fv is, now I have this curved surface, this curved surface. So now what will you consider? What will you consider? So for these cases only, just look that you can't consider any upper water surface, you can't, I mean, you cannot consider any upper imaginary fluid mass, that is any fluid mass that is above this surface, because you don't have any fluid there. So you are bound to consider this surface, this form, this imaginary fluid mass. Okay, and now you only know that if I draw this imaginary fluid mass here, okay, then again in the vertical direction I have this weight, this w, or maybe it is w1, let us say, and this reaction. And how to find this reaction? Now the concept is, if if there was not the gate, then this part totally have to be filled with water, right? Have to be filled with water. Then I should have filled this much part also with my water. But in this situation, I have water only in this much part. So had I had this much part only, then this R should be is equals to this total weight of this part, right? Okay, then this R is this total weight. Then I know that from again, so this is the, let us say, if vertical, if vertical, that is the force on the fluid volume by the surface. Okay, then this if vertical is again equals to something wi minus r, that is wi minus w, that is the weight of this much amount of fluid volume, weight of this much amount of fluid volume. Okay, that means in the diagram, the weight of this much amount of fluid volume. So I have to calculate this volume, and it is not a very difficult task. That is the area, that is pi r square by 4, because it is the quarter area, into the width, that is the volume, into rho g. So this will be the fv. So you can have two situations, one like this, one like this, that you have this free surface. Okay, you have this free surface and your curved surface is like this when you have your upper liquid. Okay, your upper imaginary fluid mass. Just remember, you have to consider always from the free surface. Okay, and you also can have a situation like this, a situation like this, where you don't have the upper surface or upper imaginary fluid volume. For both the cases, what you have to do is, when you don't have this upper surface, just extend this free surface. Okay, just extend this free surface and look that uh, what is the end point of the fluid domain. It is this. And now just just consider just consider or just think that I have the fluid all over this gate now up to this point. So this point is very important. Then you have to calculate the weight of this much part only, that is above the domain. So if you considered this point and you have considered, let us say, this much of fluid domain and you have considered this all volume, then that will be wrong. You only have to consider up to this point. So that is the end of the physical fluid domain, end of the fluid domain that I have been given in the problem. So you have to consider only this volume. So the first step is, remember, extend the free surface, then find the end of the physical fluid domain of the problem, then draw a vertical line to close that. So now this is your actual fluid domain for your problem analysis, not actual fluid domain for your problem analysis. If you have to calculate the vertical component of the force on this surface, then consider the fluid imaginary mass that is above the surface. And if you have this much, this case, that is you have this upper imaginary fluid surface, then that is fine. Just just consider this weight, right? So I have conveyed you the trick or the method by which you have to go in the exam, and as well as I have conveyed you the whole concept. Don't forget the whole concept. Just try to derive the expression by your own in your own copy, and by the first principle, that is the principle of static equilibrium and the Newton's third law of motion. Okay, I want all of you to do this for your own sake. Then if in the examination hall, if you forget the approach or you forget the formula, then you can derive the approach or formula by yourself. So just make sure that you share the videos to your friends or your junior or to whomever who need this. And you can subscribe if you want, but that's not the uh, important thing. That is all your wish. And so just comment if you have any suggestion on this, that I can improve my style or anything. Okay, and just feel free to communicate with me in the comments. So up till next time, goodbye and take care. Thank you.